of t, it's going to be units per time. So we're keeping that kind of generic. It could be meters per second, it could be cars per minute, whatever. But we're going to just kind of keep it general. Okay, so if it's units per time, r prime of t would represent, what would the units be for that? Yes, good. So r prime of t is going to represent the rate that r of t is changing, and it would be in units per time squared. So if original was meters per second, the derivative would be meters per second squared. Okay, now let's do integral a to b. So remember, an integral is an area, so you would be multiplying the units. So if this is units per time, we'll say that's my height, and then I multiply that by time, what would be left over? So we'll do length times width, right, because it's area. Area equals, so it would be units per time multiplied by time. What's going to happen with your times? Cross out. So if it was originally meters per second, now it's just going to be meters. If it was originally cars per hour, now it's just going to be cars. Okay, so this would be the number of units accumulated over 0 to b, or a to b. Okay? Now, 1 over b minus a, that's one of your antiderivative thingies that we learned. So what does that represent? That's one of your special, it has an average in it. Okay, I'll just tell you the average value of r of t over a to b. And now think about, if it's average value, that's the same as the average y value, so your units will stay the same. So if r was in units per time, then the average value will also be in units per time. Okay? And then your last one, version B, just remember that that's a thing, you should know it. Okay? So remember, average value, the units stay the same. Derivative or a slope, you get units per second squared. Okay, and then for integral, the time bumps off. Alright, so take a look at the first example. So it says, a particle moves along a line so that the velocity is given by, boom. Then it says, find the average velocity. Okay, so if I have velocity and I want average velocity, what are we finding? This is velocity, we want average velocity. Which one? Would that, it has an average in it, so it's either average rate of change or average value. Which one? Average value. Because think about, value means y value, right? This is velocity, that's velocity, blah, 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 velocity, so they're the same. So I do 1 over 5 minus 2 integral 2 to 5 of velocity, which is root 2t minus 1. Okay, then just to make sure that we're practicing typing all this stuff in, go ahead and type that one in for me. So in the front, you can reduce that. 1 over 5 minus 2 is going to be 1/3. Then remember, it's math 9 from there. And then you're going 2 to 5, square root, 2x minus 1. Okay, so the average value on that interval would be about 2.4226. Okay? And then since that's average velocity, just for fun, let's say that's meters per second. Okay, because it's still velocity, it's just the average velocity. Okay, then go down to part B. Now we want average acceleration. Okay, average acceleration is going to be the average rate of change. Because remember, a rate of change and a slope, those are the exact same thing. So I would do v of 5 minus v of 2 over 5 minus 2. Now, if you have not already, go ahead and type that equation into y equals. We're just going to review the shortcuts for that. So y equals, I'm typing in square root 2x minus 1. Okay, then from there, after you type it into y equals, remember how to pull the fraction bar up? It's alpha window, nope, not that one, alpha y equals, and then you'll get your n over d. So remember, it's alpha y equals n over d, that pulls your fraction up. Then for your shortcut, you're going to do alpha trace y1 of 5 minus alpha trace y1 at 2, and then over 5 minus 2. Okay, so remember, all that kind of stuff is going to save you time, especially on the calculator parts. So we got 0.4226. Now let's talk about units. On the top was velocity, that's meters per second. On the bottom was seconds, so the average rate of change or acceleration would be meters per second squared. Okay, now part C. This time I wanted the average acceleration over an interval of time. This time I want an instantaneous acceleration. That is the same as a derivative. And so remember, in the calculator you can find the derivative using math 8. So math 9 is an integral, math 8 is a derivative. So I'm going to do math 8 here. I want d dx in the box. Alpha trace y1 in the big box, and then I put where I want the derivative, which is at 5. So 0.333333. So acceleration at 5 equals v prime of 5, which is 0.3. And you could put 3 repeating with the little line, or 0.3. Okay, last one like that. Look at part D. Says, given that x of 2 is 8, find the position at 5. So this is your version B. When do I have the position? When do we already have it? At x of 2. When do we want it? X of 5. So it would be x of 5 equals x of 2 plus integral 2 till 5. And then in here you'd put your velocity. Okay, so type that in and then add x of 2 to it. Yep, looks good. So x of 2 we already know is 8 plus, and then that integral, remember, you wouldn't do it by hand, you do it in your calculator. So 2 to 5, alpha trace y1, and then dx. You can. So 7.2679. Now I forgot to add 8 to that, so I'm going to do that next. So my total is 15.2679. Make sense? Remember all that? All the calculator stuff? Okay, so go ahead and turn to the next one. Hang on one second. Okay, why don't you try number 2, parts A and B. And then I'll come bring y'all a little cookie, okay? So first thing you can do is type the equation in. One of them you're going to be doing an average on, so you only have 2 choices there, average rate of change or average value. Like this one, so if it's a 3 in the front, you have to log 3. Now keep in mind if there's a 3 in front, you have a 2. You have to divide by a 2 to turn it into a 5. And then log 3. Or like on this one, since the base was 2, we have to log 2. Okay, so what did they give you? They gave you the velocity when? The velocity at? Yup. And then when do you want the velocity at? 3, so that's in version B. So you have the velocity at 0, that was given to you. You want the velocity at 3, so you're setting up a version B there. You can have 2 if you want. Yeah, mine you want one? Sure. Yeah. You guys can have 2 if you want for being so dedicated. One. Okay. And then the integral you'll do is you want another one? Okay. Want 1 or 2? Okay. You're welcome. Okay, then think about what you would set up in part B after you finish part A. Want 2?
Sure.
Go. Go.
Oh, thank you.
Gas going? You want to? I met your brother yesterday.
Oh, yeah.
So much alike. It like freaks me out because I couldn't think of who he looks like, and then when he said he was your brother, I was like, oh.
I'm surprised you haven't met before because I thought he was
I
in
feel
New
like I
Alpha
have
Theta.
met him. Yes, probably from New Alpha Theta. But I guess since I hadn't ever seen you all together, I just hadn't like connected the dots. You know? So you should have this. Velocity at 3 is velocity at 0 plus the integral 0 to 3 of your function. Then this part you would have done in the calculator and then added it to 5. Okay? Anybody got the answer yet? 11E. Sweet. Okay, next one. I have acceleration. I want average acceleration. What am I finding? Is it A rock or average value?
A rock.
Okay, so it's only A rock if it's a rate of change. That's what the rock part stands for. So think about, if this is acceleration and I want average acceleration, is that a slope? No, that's an average y value because these match. So anytime that the average that you want is the function you already have, it's the 1 over b minus a thing. So it'd be 1 over 3 minus 0, integral 0 to 3, a of t dt. So that's where you have to remember, rate of change means slope. So if you have on the one right before that, okay, you had velocity. So average acceleration would be the average slope because acceleration is the slope of velocity, right? Okay, and then you can type that in if you want to. Okay, go down to the next one. I'm going to give you a minute to read through it. Okay, this is off of one of the old multiple choice tests. So it says the cost in dollars to shred a confidential document of a company is modeled by C, a differentiable function of the weight of the documents in pounds. What is the best interpretation of C prime of 500 equals 80? So the first thing that I would look at right here is, what does it say that cost is measured in? What is it measured in? Dollars. So C of T is measured in dollars. So then think about, if I want C prime, that should be dollars per something, right? Okay, automatically you know that. So it says the cost to shred 500 pounds of documents is 80. The average cost to shred documents is 80 per 500. Okay, increasing the weight of the documents by 500 pounds will increase the cost. Or the cost to shred the documents is increasing at a rate of $80 per pound when the weight of the documents is 500. Okay, so pretend it's the AP test, read through them again if you need to, and then pick which one you think might be right.
don't have to use the shortcut.
Okay, thoughts? What do we think it is? Any we can for sure eliminate? Okay, we can eliminate B. Now, B has dollars per pound. Here's the problem. It says average. Did they put a 1 over B minus A in front of it? Then there's nothing to do with average. Okay? Any other thoughts? We have a C prime. So what should the magic word be? A rate. Okay, and then why is it increasing? Because the rate came out to be positive 80. And then remember that if C is in dollars, then my derivative would be in dollars per pound. So D is going to be correct there. Now, notice if I change to this one. Okay, this is the same. A lot of times on the AP test, they'll do this, where they'll do, instead of writing 1 over 500, 0 to 500, they'll just put it all together in one fraction. So note that these are the same. One of them, they're putting the integral on top of the 500, but it's just a different representation of the same thing. So rewriting it like this, what is this the formula for? This would be the average, right? That's average value. Now, what's in the middle? Cost. Well, then this is the average cost. So whatever you have in the middle, the average value of it is the same thing. So we would say the average value of the cost function, C of t, is $44 over 0 to 500, and then that's measured in pounds of paper. Okay, so if they do a 1 over B minus A, you're doing the average of the thing that's already in the middle. So if this is the cost at how much it is for the paper per pound or whatever, then this is the average cost it would take to shred 500 pounds of paper. Okay? Good. All right, turn the page. Okay, so next one, we have a chart this time. Okay, so it says, as a pot of tea cools, the temperature of the tea is modeled by a differential equation H. T is measured in minutes. Temperature is measured in degrees Celsius. Values are in the table above. Okay, part A. Use the data in the table to approximate the rate. Remember that a rate is a slope, which normally means that you'd be taking the derivative, but you don't have an equation. What other type of rate besides a derivative do you have? The average rate of change. Very good. Remember that average rate of change is a type of slope. Okay? Then it says we want it at 3.5. Well, then where am I going to take the average rate of change if I want to average it at 3.5? Between what two values? 2 to 5. Very good. Okay? So if I want the slope at 3.5, I don't have the equation, but I can at least do the slope formula around where that would be. So I do the h of 5 minus the h of 2 over 5 minus 2. Now, notice here when it says show the computations, if you don't put those, you won't get credit on the AP test. So you want to make sure you're showing that slope formula. Okay, then our h of 5, it says, is 52. Our h of 2 is 60. And then 5 minus 2 on the bottom is 3. Now, a lot of times they'll also say to use, indicate units of measure. So what would my units be on the top if this is how hot the tea is? Degrees Celsius, right? Per, and then what was my time on the bottom when I did 5 minus 2? Per minute. Now, if I were to subtract that out, 52 minus 60, does that come out as positive or negative? Negative. Does it make sense that our rate is negative if our T, it says, is cooling? Okay, that makes sense. The temperature is decreasing. That's why we got a negative rate. Okay, go on to part B. Okay, you're going to do this one. It says, using correct units, explain the meaning of 1 over 10 integral 0 to 10 in the context of the problem. Make sure you're putting units into it and explaining what it is, and then we'll check in a second. Okay, so first thing, 1 over 10, integral 0 to 10, what is that? Yes, average value. Now, what is it the average value of? H, which is how hot the tea is, right? So that represents the average temperature of the tea. What is that measured in? Degrees Celsius over what time period? 0 to 10 minutes. Okay, and so the three things that have to be in your answer are the noun, so it's the average temperature of the tea. Okay, then your units, which would be minutes, and then degrees Celsius, and then your time, which was 0 to 10. So you want to make sure you can think about, it's a ton of things to remember. Time, units, noun. Okay? Then it says to do it. So it says, in the context of the problem, explain it. Then it says, use a trapezoidal sum with 4 subintervals. So let's review. For a trapezoidal sum, do I have the same delta x, or is it changing? Same delta x, or is it changing on each subinterval? It's changing. So remember, it's 1/2 y1 plus y2 delta x. That's your formula for a trapezoidal sum. So if I was wanting to set this up, I'm going to squeeze it in right here underneath part B. From 0 to 2, what are my y values? And 60, so I do 1/2, 66 plus 60, and then what's their individual width, since it's changing every time? 2, across the x-axis, right? Then 1/2. Now I'm going to add 60 and 52. 60 and 52 are my next two bases. And then from 60 to 52, what was the distance on the x-axis between 2 and 5? That would have been 3, right? Okay, then my next one, I'm doing 52 and 44. So plus 1/2, 52 plus 44. But then the width between those two from 5 to 9 is 4. And then for your last one, you're doing 44 plus 43. Remember, 1/2 still in front of that. And then the delta x from 9 to 10 would only be 1. Okay, so keep in mind that your area, if you were trying to figure that out, would be a trapezoidal sum. Now, if I leave it like that, I'm going to get it wrong. What am I missing that they asked me to find? All of this crap is an estimation of the integral portion. What did they put in front of the integral that I have to put in front of my trapezoidal sum? The 1/10. Very good. So the trick there was that you'd be like, oh, trapezoidal, I know how to do it. But remember, in front of that integral, they put a 1/10 there. Well, then I need to put a 1/10 outside of mine as well. Okay, so make sure you're going to estimate it using the trapezoidal sum, but if it's an average, you need to keep that 1/10 in front of it. Okay, part C says, evaluate the integral of h prime. Using correct units, explain the meaning of the expression in the context of the problem. Okay, so first thing, you have an integral of h prime. What is the antiderivative of h prime? We're going to put it in brackets. What is the antiderivative of h prime? Normal h. Good. So h of t is in the middle. And then what two values are we plugging in on top? Top we're plugging in 10. Bottom we're plugging in 0. So it'll be h of 10 minus h of 0. Then look at your chart. What's h of 10? 43 minus, what's h of 0? 66. And 43 minus 66, you could honestly just leave it like that if you want to. Okay, but it'll come out to be negative 23. What would that be measured in if I was plugging into h? If these were both H's, what were they measured in? What's H measured in? Degrees Celsius. So then if I'm subtracting two things, that doesn't change your units. So your answer would be degrees Celsius as well. Now it says explain the meaning. What is the meaning if I take the temperature at the end and I minus the temperature at the beginning? What is that telling you? How much the temperature went down over that time period, right? So that means over 0 to 10 minutes, the temperature dropped 23 degrees Celsius. And then just make sure you're hitting those key things. You have to put units, you have to put what changed. In this case, it's the temperature of the T. Okay, and then the time frame as well. Okay? Alright, part D. Part D says, at time 0, biscuits with a temperature of 100 degrees Celsius were removed from the oven. Temperature of the biscuits is modeled by a differentiable function b, for which b prime equals blah blah blah. Using the given model at time t equals 10, how much cooler are the biscuits than the T? Okay, well, first question, how hot is the T at 10? We already know this. Okay, very good. 43 degrees, right? We already figured that out. It's in the table. We already know how hot the T is. So the question is, how hot are the biscuits? Okay, so to find the heat of the biscuits, what time do you know for the biscuits? The biscuits at 0, how hot were they? 100, that's what you have. Then what do you want? The biscuits when? At 10. So this is a version B. So I do the biscuits of 10 equals the biscuits of 0 plus the integral from 0 to 10. And remember, whatever goes in here should be the derivative of what's on the outside. So if these are biscuits, then on the inside should be B prime. And notice that's exactly what they gave you. Right? So B of 0, we said the biscuits at 0 were 100 plus. And then this integral I would do in the calculator. So when I type it in, I'm going to go ahead and do 100 plus in front of my integral so I don't have to remember to add it later. What? Oh, I typed it in wrong, that's why. Okay, typing that in, you should get the biscuits are 34, yeah? Okay, so my biscuits are 34.1827 degrees Celsius. So then does that fully answer my question? You got to subtract, because the question was how much hotter or how much cooler are the biscuits. So then your final answer, you'd have to subtract those guys. So I'm going to minus 43 from my answer, and I get 8.81724 degrees Celsius. And I did an extra number, but you don't really need the 4. Okay? And then that would be cooler than the T. Okay? Alright, turn the page. Okay, which one do I pick? We probably only have time for one more. Let's do this one. So you're going to skip that one and go to this one. Okay, so it says, a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries in a special box from noon until 8 p.m. The number of entries in the box afternoon is modeled by a differential equation, 0 to 8. E of t in hundreds of entries at various times are shown in the table above. Okay, part A. Use the data in the table to approximate the rate in entries per hour at which the entries were being deposited at 6. Okay, first thing you should think about is that a rate is a slope. There are two types. There's a derivative, which is a slope, and an average rate of change, which is a slope. Which one are we going to do here? If you have a table, hint, you can't do a derivative, so it has to be the average one. So that'd be average rate of change, and then where does 6 fit into the table? From 5 to 7. Okay, remember, show the computations. That means you do have to set it up. Remember, I'm going to call my function e because that's what it's called in my table. So it would be for part A, e of 7 minus e of 5 over 7 minus 5. E of 7 is 21. E of 5 is 13. Bottom comes out to be 2. And I don't really have to subtract it. You can if you want to, but you don't have to. Now notice on this one, they gave you the units right here. Okay, but you should still think about, a lot of times they won't. It'd be hundreds of entries per hour. So that's how fast they're being deposited. Hundreds of entries per hour. But remember, your units are just y over x because it's rise over run. It's a slope. Okay? 21 minus 13 gives me 8. So 8 divided by 2 is 4. So 4 hundreds of entries per hour. That would be your thing. Okay? Alright, part B. Notice this should look familiar. This is what you just did on the other thing. Whenever you see them doing this over and over again, it will probably be on your AP test too. So it says, use a trapezoidal sum with 4 subintervals given by the table to approximate. It's not just an integral, it's an integral with an 8th in front of it. So that means that when I set it up, I need to remember to put that 8th here in the front. So I'm going to do part B right here. I'm going to write the 8th before I set up my trapezoidal rule. Okay, then remember you're going to do 1/2, add the y values, so 0 plus 4, multiply by the width, 0 to 2 is 2. Next trapezoid, 1/2, add the y values, that'd be 4 plus 13. Then multiply by the width between the x values, which is 3. Next one would be 13 and 21, 1/2. And then 5 to 7, your width is how far? Plus, last one, 21 and 23. And then your x value distance is 1. But then remember that 1/8 has to be out there in the front. Okay? Now, the second part of the question says, using correct units, explain the meaning. Okay, so go ahead and write that out, and then we'll check it in a second. So it's 1/8 integral 0 to 8. Yep.
Because it doubles the y.
And then it's every 10 years, so it's every 10.
Okay, and then on this one, I did this, I got a negative.
You shouldn't have done it. Oh, because you forgot the 1 plus. It shouldn't just be 0.04. It should be 1.04. Remember, you're adding it to 1.
Oh, okay.
So that's why it messed up your base. And you'll have to change your part B too. That should be a 1.04 there before you type it in.
Okay. And then for this one, is this
You have to combine these first. So remember, if they're added, you're going to multiply 2 times x minus 1. So you'll have to distribute.
So it'll be
Make it 1 log, and then you
2x
can leave
minus
both sides.
2.
And then you can get rid of the log after. Okay, so integral, blah, 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 represents, what'd you put? Anyone can tell me what you put? Yes, the average value of what? What's in the chart? Hundreds of entries, right? Over what time period? 0 to 8 measured in hours. Very good. So, the average number of entries, and then I'm going to put in hundreds just because since they're measuring it in hundreds, I don't want to leave that out. So it's the average number of entries in hundreds, okay, over the time period from 0 to 8 hours. Okay, or if you wanted to, you could have said from noon to 8 p.m. if you like that better, that's fine. Okay, part C. At 8 p.m., volunteers begin to process the entries. They process the entries at a rate modeled by the function P, blah, 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 blah. Hundreds of entries per hour from 8 to 12. According to the model, how many entries had not yet been processed at midnight? Okay, so two things going on. The visitors are taking their entries, they're putting them in the box. Then as they're processed, what's happening? They're coming out of the box. So, if I want to know how many have not been processed, what do I need to do with those two numbers? Okay, number entries going into the box, then they're being processed and taken back out of the box. If I want to know how many are left over, what am I going to need to do with those? Subtract. So, first thing I want you to do is add this up, because we need to know how many entries are in the box to begin with. So you're going to put in, actually, and then should you type it in with the 8th in the front? No, don't type it in with the 8th in the front, because we don't want the average. We want to know how many entries were there. So no 8th, you're typing in the rest of it though. Uh-huh.
I think I did something wrong on number 1, but I can't quite.
Oh, you're right. That's right. I forgot to tell you. It's in here. That's right. The correct answer's not there.
Alright, thank you.
Uh-huh. Okay, did you get 85.5?
What do I turn it in?
Oh, you just put it on my desk right there.
Thank you.
85.5, yeah, so that's how many entries were turned in. Now keep in mind that's in hundreds, right? Okay, so then how am I going to find out how many were processed? Well, this tells me how many were processed per hour. So if I want to know how many were processed, what do I need to do over the interval from 8 to 12? I need to do a what? If it's entries per hour and I want to know how many entries, I need to do the, not the derivative, the integral. So to know how many were processed, total processed, I need to do the integral. Now, when were they processed from? They weren't processing them until the zoo closed. They started processing them at 8 and they went till 12. So 8 to 12, P of t dt. Okay, then you'll do math 9 and then type it in. You can put the equation into y equals if you want to, but it won't really make it that much faster. Okay, you should get a nice, easy whole number for that one. How many entries had they processed? 16? Okay, good. So then think about if this is how many they got, this is how many they processed, then how many have they not yet processed? We would have to do what as our last step? Subtract these guys. Very good. So then for that last step, I'd do 85.5 minus 16. That means that there were 69.5 hundreds of entries not processed yet. Okay? Alright, then the last part, part D says, according to the model, At what time were the entries being processed the most quickly? Okay, so first thing we want to think about is we're looking for a max, right? Okay, so what I want you to do is take this equation. This is already in entries per hour. If we want to know when they're being processed the quickest, we want to know when we have a min or a max. Which one? A max. Very good. So take your graph. Okay, go ahead and type it into y equals. Okay, then remember, what is our window that we're considering this graph for? Only 8 to 12. Very good. Oh, wait, and then hold on. If we want a max, what do we have to do first? I forgot to tell you to do. Take the what? You don't want to graph the function, you want to graph the derivative, right? So take the derivative first and then graph that, sorry. If we want to know when they're processed the quickest and we're looking for a max, we need to find p prime and then take the derivative of that. So p prime of x, notice they gave you a super easy function. Okay, it'd be 3t squared 60t plus 298. Okay, so remember, anytime you're looking for a max, you're taking the derivative and then looking for the sign change. Okay, then here's my graph. Notice I already changed my window to be only from 8 to 12. So I'm looking for where it hits a maximum value. Where does that happen at? So I would hit second trace here, and then I'd be finding that x-intercept. So I'd go down to 0. Then my left bound, I want to be, this is the max, right? Because it goes from above to below. This one over here is a min, so we don't want that. So I'll go a little bit above to the left, push enter. Little bit below on the right, push enter, and so my max occurs at 9.1835. So I would say I have a relative max at t equals 9.1835. Okay, then because p prime changes from plus to minus. And remember, that's consistent with a max. If it's changing from positive to negative, that means we have a max at that point. Now, quick question. I'm not going to make you finish it, but are there any other times that we have to consider besides the relative max? How do you know that it's the real max? You would have to compare it to what? In a chart. What else would you have to compare it to? Because this is the relative max, but we need to make sure that it's the real max, the absolute max. What else would go in my table besides 9.1835? The endpoints. Very good. And what are the endpoints for that function? 8 and 12. Very good. And then where would you be plugging those into? Not to p prime, but back into p of t. So just remember, you would find what those are, what those critical numbers are, and then you'd have to double check these numbers, because just because it's the relative max, it doesn't mean that it's the real max. Okay? Good job.